Welcome. What you may have noticed is that almost all batteries have a metal that does all the chemistry. Different metals react at different reaction potentials, and lithium has one of the highest when we consider it per atom, minus 3.04 volts. Also, a lithium atom and ion are the smallest of any metal. This is one of the reasons why the lithium-ion battery can contain a lot of energy. They have a high energy density. In this video, we will discuss the basics of lithium-ion batteries, the powerhouse batteries we know from our laptops, phones, and electric cars. Actually, there are many different lithium-ion batteries on the market. It is therefore better to talk about them as a family of batteries. In all these types, lithium is the driving force of the battery. The different family members have different cathodes and anodes. This results in different battery properties that make them interesting for different applications. The first battery to hit the market was the battery that has a cobalt oxide cathode and a graphite anode. We will use this battery to explore the chemistry of this battery. The metallic lithium is dispersed in the graphite. One could say that chemistry-wise we can ignore the graphite. When we discharge this battery, lithium atoms are oxidized. The electron is going through the external circuit and powers our device or car. Then it will travel further towards the cathode. In the cathode we have cobalt oxide. And if we then zoom in on the cobalt, it is charged 4+. The cobalt will take up the electron and becomes 3+. Cobalt is here reduced. Since the cathode is becoming now negatively charged, the lithium ions will go through the electrolyte towards the cathode to stabilize this negative charge. The beauty of cobalt oxide crystals is that they have little spots in their crystal structure to accommodate this lithium ion. A lot of research has been done on the cathode material. Although this type of cathode provides very high energy density, it lacks in cycle lifetime. And cobalt is an expensive metal that is considered critical by the European Commission. Later commercialized cathodes are iron phosphate, manganese oxide, nickel manganese cobalt oxide, and they all have their pros and cons. And they all have found their place in the market. Researchers are also looking at the use of sulfur or oxygen as cathode, but this is still far from commercialization. When we look at the anode, one could argue that we just have to use metallic lithium. This is very true and is heavily investigated by researchers. However, until now, metallic lithium tends to give dangerous batteries because of lithium dendrite formation. Over many cycles, lithium is not uniformly packed back in the anode. It will make many different tree-like structures. When these grow, at some point they will touch the cathode, which will cause the battery to shortcut, which can result in fires. Therefore, lithium is dispersed between graphite. This will lower the energy density, but will give much safer and more stable batteries. Recently, silicon is commercially available as an anode material. It has a much higher energy density than graphite. Previously, silicon suffered from the fact that its volume heavily increased when it is absorbing lithium. It led to a lot of mechanical stress on the battery. But now, due to clever engineering, manufacturers are able to mitigate the volume expense. Different energy storage applications need different solutions. Although lithium-ion batteries have a great power density, they are relatively expensive and they do pose safety concerns. There has been a lot of progress on flammability, but the risk can only be minimized and mitigated. It therefore stands that lithium-ion batteries are best suited for high energy density applications, which are mobile applications like electronics and electric cars. Since they are a very mature technology, large-scale energy storage is also being investigated with lithium-ion batteries. But in that segment, price is very important, which, as we discussed, is a weak point of this technology. Recycling of lithium-ion batteries is not only important for environmental reasons. As we have seen, lithium-ion batteries contain many elements that are rare and/or expensive. Many of these elements are legislated through the EU Critical Raw Materials Act. This adds an extra dimension to recycling. Although the recycling infrastructure is still largely under development, the process is as follows. First, the batteries are collected and safely discharged. Then they will undergo mechanical processing, they are crushed, and this is then followed by hydrometallurgy or pyrometallurgy, which is used to fish out specific metals. These metals can then be further purified and be used again for new batteries or other applications. The variety of lithium-ion chemistries is complicating the recycling process, and therefore the EU has implemented the battery passport. Batteries that are bigger than 2 kilowatt-hours or are used in transport need to have a document that clearly states the chemistry and other details about the battery origin and what happened during its lifetime. Together with other strict regulation, it will support the implementation of a good recycling infrastructure for lithium-ion batteries, just as lead-acid batteries already have.